curved. So that's fine up to 7 lines. It turns out there's a theorem that says any configuration with up to 7 lines, you can make, even if they're curved, you can draw it with straight lines. There's a paper on the archive from 2012. So there's a lot of work to be done there. And then you can do the same thing with circles. So how many ways are there to draw n circles in a plane? If you don't allow tangencies. If you've got 3, so again we're in the affine plane. If you've got 2 circles, they can either be disjoint, one contain the other, or they can be 2 points. So there are 3 ways of drawing 2 circles. And 14 ways of drawing 3 circles and 168 4 circles. And we don't know. And what if you allow tangencies? So, change the subject. So, there's a contributor, Eric Angelini, who is in Brussels, who has sent in many wonderful sequences. And here's one of his that I really like. It's a sequence, it starts with 0, and the rule, I guess that would be implied by the rule. So the rule is, let's say we impose the restriction, we start with 0. The rule is, if you look at the combined digits of 2 successive terms, they should be rearrangeable to form a palindrome. And you always take the smallest number that's not already in the sequence. So we start with 0. We could have taken the next number to be 1, but you can't make a palindrome out of 0 and 1. Or 0 and 2, or 0 and 3, or 0 and 10. Why isn't that 10?
What about 10?
0.
Yes.
0, 1, 0 starts with a 0.
That's not allowed.
So you can't do that.
So we have to go to 11. 11 works because 1, 0,
1, 0, 1.
And then after that, we can have 1 can be used because 1, 1, 1 is a palindrome. And then 10.
So we should say a palindromic integer.
A palindromic
rather than a palindromic sequence of digits. To clarify that.
And anyway, it grows after a while. You see a 2 and a 3 and a 4. So in base 10, it looks like this. And you can do this in any base. And just as happened to me last night, get some water. This is one of those sequences that wakes you up in the night. It woke me up in the night with a proof. Oh, so here's a picture of it. It's got a rather nice looking graph. You can see the first 200 terms on top, and then the bottom picture shows you 10,000 terms. So look at this graph. It's quite remarkable. You don't often see a graph that looks like that. Anyway, you can prove that in fact every number appears. This is in base 10 or any particular base you like to choose. This is a permutation of the infinite, of the non-negative integers. So we started with 0. And the proof, I don't know if you want to see another proof. There's a proof. It's a very nice proof. You look at the parity. You look at the condition of when 2 numbers can be put together to make a palindrome. To make a palindrome out of a number, you either have got to have an even number of copies of each digit, or you can have at most 1 digit appearing an odd number of times, and you put that in the middle. Otherwise, all the digits have to be paired up. So you've got to have an even number. So when you put the 2 numbers together, either you have the parity of the numbers of letters that you see, either even, or you can have at most 1 odd number. So you map. So you look at the parity of this, and you map n into a vertex. In this case, in base 10, you map it to a vertex of a 10-dimensional cube, and you draw a graph whose vertices are the points of the cube, and you join two vertices if and only if the Hamming distance is 0 or 1. But 0 means you have a loop, which Hamming distance 1 is Hamming distance 1, like in the normal skeleton of the cube. Then you say that because of the rule of construction, the sequence traces out a continuous path through the vertices of the cube. Now, if a number was missing, well, so because it's an infinite sequence, at least one vertex appears infinitely often. And so any vertex adjacent to one that appears infinitely often actually has to appear infinitely often also. Since iterating that, since the graph is connected, every node has to appear infinitely often. But if there was a number that was missing, it's easy to see that means that that node would not, that it can't happen. Yeah, so what happened last night was that this is a sequence, a frequent contributor from years ago called Amanat Murti wrote to me and said, "Happy birthday. We haven't been in touch for 5 years or more, but here's a new sequence that I haven't sent in yet." He didn't even offer to send it in. He hasn't been involved in the OEIS for some years, but he did send me an email. Oh, and I also got a message from Riga saying happy birthday. I wanted to say that we have a community all over the world. This is, I was going to say various things about our modest contribution towards world peace is the OEIS, because we really are an international community. So this sequence came in from Mumbai, where Murti lives, and the sequence is, again, it's a recurrence, like many of these really interesting sequences. And here's the rule for this sequence. We begin with 2, and the rule is that the nth term has to be relatively prime to the next n terms. So the first term is 2, and it has to be, that's the 1st term, so it has to be relatively prime to the next 1 terms. And you always take the smallest number that hasn't appeared yet, and it's different from any number that you've seen already. So we could put it, and it's bigger than 1. So we could put a 3 here, because we haven't seen a 3 before, and 2 and 3 are relatively prime. So the next term is 3. Now, the rule is that 3 has to be relatively prime to the next 2 terms, and 4 and 5 will. And then 4 has to be relatively prime to the next 3 terms. So 5, 7, and 9 will. And so on. And here you get an 8, and it's not monotonic, and it goes up and down. So I created a sequence for this, A247 665. You can look it up. And one of our editors, Jens Cruz Anderson, wrote a parity program to work out the first 1,000 terms. And I stared at it and noticed that some numbers were missing. 6 in particular was missing. So last night I mentioned this to Russ, and Russ Cox in the front row, and he went away in about half an hour. He computed 5 million terms using his language Go. And again, 6 didn't appear, 12 doesn't appear, at least in the first 5 billion terms. So at 3 o'clock this morning, I woke up and said, now that we know that 6 probably doesn't exist, let's prove it. And so, so I can actually prove that 6 doesn't exist. In fact, there are no numbers that are products of powers of 2 and powers of 3. And probably with a bit more work, I'm looking Jeff, a little help here, this needs a bit of hard analytic number theory, yeah? That we can prove that for any, that there are almost no composite numbers in this sequence. You can prove that prime powers appear, and that probably almost no composite numbers are going to appear. There's a, did I have a graph? Yes, sorry. Okay, so here's a graph of the first 200 terms. And they're pretty much all primes, except for a few drops, a few spots down here. So I think with a bit of work we can solve that. Read Kelly's sequence, I think it's pathological arithmetic, which I'm not going to talk about, even though it's really sick and interesting. Carryless arithmetic. 19 plus 31 is 40. Okay, because there are no carries. And lunar arithmetic, there are no carries, and you do it digit by digit, and plus is max, and multiply is min. So here 19 plus 31 is 39, because 9 plus 1 is the maximum of 1 and 9, it's 9. 1 plus 3 is the maximum of 1 and 3. So 39. Those are the rules for lunar arithmetic, formerly known as dismal arithmetic. Anyway, so somebody sent in a sequence recently for what you might call zeroless arithmetic, which is you carry out the normal operations and then you throw away any zeros. So zeroless factorials, instead of 120, you get 12. So it's really sick. I've been looking. I just want to report briefly on some work that I've been doing. Jerome, how long do I have? Are we going to finish?
Yeah.
10. I've been looking at cellular automata. And of course, many people have looked at these things. But I've been looking at the question of how many cells are on if you start with one on cell and let the automaton run for a while. So rule 30, the famous rule 30, looks like if you let it run, it's obviously totally random, and it's on the front cover of Stephen Wolfram's book, A New Kind of Science. You can't expect to explain the innards of this. But what about the number of cells that are on? Well, if you start with one cell, and it seems to grow pretty linearly, it would be nice to know more about that particular sequence. But there are other sequences. Of the 256 one-dimensional array 3 cellular automata, there are 7 that seem the most interesting. There's rules 30 and 110. Rule 18 is pretty nice. The number of cells that are on is 2 to the power the weight of n. This is the Pascal triangle mod 2 picture. And the rule here is you turn on if and only if either your left neighbor is on or your right neighbor is on. So it goes like that. And the number of on cells, the sequence, which is A1316, goes 1, 2, 2, 4, 2, 4, 4, 8, 2, 4, 4, 8, 4, 8, 8, 16. It grows in blocks of 2, successive powers of 2. And this seems to happen with many cellular automata. And I don't really understand why that should be the case. But I have some partial results about that, which originated by looking at Rule 150. And Rule 150 is you turn on if and only if an odd number of your neighbors are on. And the neighbor, in this case, is 3 adjacent cells. And you can explain this. And this was analyzed by Torsten Silke in about 2001. And he found a formula for the nth term. Namely, if you take, this is equivalent to what he did, if you take the not polynomial, the Lorentz series, 1 over x plus 1 plus x, raise it to the nth power, and look at the number of non-zero terms. that's the sequence. And if you want to know what is the nth term, if you write n in binary and look at the runs of ones in the binary expansion of n, then that determines the sequence. So there's a formula that the nth term, there's an underlying sequence, which is the Jakob-style sequence, 1045, and the nth term depends on the product of the Jakob-style sequence evaluated at the lengths of the runs of ones in the binary expansion. So I generalize this something called the run length transform. You can do this for any sequence. So, since I don't have much time, I spent quite a bit of time trying to understand the sequence A160239. You remember when you were visiting, Charles, you showed me how to work out what the rule, how we could do this in Mathematica. And, Mathematica is wonderful for producing pictures of these algorithms. But it took me until last week to figure out how 160239 works. This is a simpler version. I just wanted to show you some pictures. This is a different one. This is rule 614, 63rd generation. And you get a very nice recurrence. This is a picture of the 63rd generation of the cellular automaton rule 614, which is defined, you turn on if an odd number of your neighbors are on. But neighbor means the, what's it called, the von Neumann neighborhood of the cell. It's the north, south, east, west neighbors plus the center. It's a 5-cell neighborhood. And you get a recurrence by looking at the picture and cutting it up and decomposing it and figuring out how the 63rd generation relates to earlier generations. The one I was really interested in was Fredkin's replicator, which is sequence 160239. It's the run length transform of a certain sequence, except that I didn't have a proof of this. But now I do, and it's based on dissecting so this is the 31 generation. And if you cut it up, and you have to use a knife to cut this up into pieces with a recurrence, to get a recurrence. And so that finally worked. Others look very pretty, but don't seem to have any rule. This is rule 780. It begins nicely, very simple, but then it gets very complicated. So I've been working with Max Alexeyev on Kaprekar's problem, and there's a poster in the poster session, so I don't really have time to talk about that. I wanted to just mention in the last, I may run over a little bit, I'm sorry to run. I want to mention some examples of music and videos. So, you know, you can click on listen. We have 2 new keywords, by the way, here and look. If you see those keywords, that means, here means it's worth listening, worth clicking on the listen button, and look means it's worth looking at the graph. Clicking on the graph. So here, I just want to let you hear a couple of sequences. This is Pascal's triangle. It's fairly typical. It has some attractive features, but it basically sounds horrible. Here's the Hofstadter Q sequence. And so they're a lot like that. Now, here's the weight of n, and 4 to the weight of n turns out a keynote, if you put two sound links, it will play them on top of each other. So I didn't know you could do this. It's a nice way. Mostly you get garbage if you do this. If you take two sequences that are related, you can play one with one MIDI instrument and another with a different. So this is combining a taiko drum and a xylophone with wave N and forward wave N. The next one is not done using. I would like to have more like this. This was a bit done by hand. All right, and then here's Rachmaninoff. The examples. This is what we want. All right, and there are various videos about sequences that I was going to show. I'll just do one because.
Yeah, the best person. I know it's not better, but you all the time.
Oh, thank you. So we've got about 160 links to animations and videos and things. This is just one example. It's some version of the Fibonacci. The first one is a fairly straightforward lecture about the Fibonacci numbers. The second one is the Fibonacci tree growing with 1 and then 2 and then 3 and 5 and 8. You see the tree growing. The third one is more artistic, very nice. And the last one is Gordon Hamilton's video about the Reckermann sequence, which he calls the Reckerborn sequence. And I should say that Gordon and I are organizing a conference in Banff next year. We're trying to get more integer sequences into the school. That school teachers, high school teachers, elementary school teachers know about sequences, that they could use them in their classes. So there's a conference. If any of you are interested in participating in this, it will be in Banff early next March, I think, of next year. It's called the K13 conference. We're trying to pick out 13 sequences that teachers might be able to use in schools. So let me show you the last thing is Hamilton's sequence.
For all of you teachers who have a number line in your classroom and use it to teach addition and subtraction, I want to recommend a sequence to teach your students. It's Bernardo Reckermann's sequence, and here's how it goes. Each step, you're going to be stepping on the number line. On the first move, you're going to be stepping 1 space. On the second move, 2 spaces. On the third move, 3 spaces. But I'm not telling you which direction. That's where it gets interesting. You start off at 0. You can never go negative. So Your first step is length 1, so it has to be in the positive direction. So let's do that. Your second step, you're going to be moving 2. Well, where is it going to go? Well, it can't go to 1 minus 2, because that would be minus 1. So you can't do that. So it would have to be 1 plus 2, that's going to be 3. So that will go there. Now, the next one is 3. So we could go 3 minus 3, that would be 0, or 3 plus 3, that would be 6, which is correct. 3 plus 3 is correct because you can never revisit a number that you've already...
I've used up my time. Thank you.